the current will be leading the voltage. Now, when we define the power factor, we assume that it is a linear load. Okay, so in case of linear load, current is sinusoidal. So the cosine of the angle by which the current is lagging the voltage for an inductive load will define as the power factor. Now suppose the load is nonlinear load. Suppose the load is diode rectifier feeding RL load. Now in that case, if you see the source current is no longer a sine wave. The worst case will be when you take the inductance value infinite. In that case, the source current will be a square wave. Okay, and therefore it is in between square wave and sine wave. That is, either it is square wave or it is quasi sine wave or it is quasi square wave, depending upon the value of the inductance in the load. Therefore, how will you define the power factor in such a case where the load is nonlinear load? In such a case, we defined the power factor as it is displacement power factor multiplied by I1 divided by IS, where I1 is the fundamental current and IS is the total current. Now, what is displacement power factor? It is defined as the cosine of the angle by which the fundamental component of current is lagging or leading the voltage. Okay, lagging or leading the voltage. Therefore, we have to extract the fundamental component out of the square wave, and the cosine of the angle by which the fundamental component of current is lagging the voltage is known as the displacement power factor multiplied by the fundamental component of current divided by total current is the definition of the power factor in the case of nonlinear load, where I1 by IS, that is the ratio of fundamental component divided by the total current, is known as the distortion factor. Now there is one more definition, total harmonic distortion, or in short we call it TSD. TSD is very popular for defining the measure of closeness in shape between a waveform and its fundamental component. It is defined as 1 by V01. V01 is the fundamental component, and summation of V0n square, n is equal to 23n, 23 up to infinity, and square of that. Now, in most of the cases, you will find that the even harmonics are not present. It will be the odd harmonics. So it will be n is equal to 1, 3, 5, like that. For three-phase case, the first harmonic will be the fifth harmonic. So it will be 1, 5, 7, like that. Okay. So this is the definition of total harmonic distortion. Okay. Now, let us take this example. In the here, your voltage is a sinusoidal waveform and the current is a perfect square wave. This is the case when we have a RL load, diode rectifying feeding RL load, and the value of the inductance is infinite. Can you hear me? All of you? Can you hear me? Am I audible? Am I audible?
Yes, sir.
Okay. If you have any problem, then just inform me, okay? Now, we have taken a case where the voltage is sinusoidal and the current is a perfect square wave. This is the case when we have a diode rectifier feeding RL load and the value of the inductance is infinite in that case. Now, in such a case, how will you define the power factor? Let us see. Now, in this case, to define the power factor, what you have to do? Okay, so you have to find out the fundamental component out of this input current. Now the line shown by this dotted line is the fundamental component of current. Okay, so this angle between the voltage Vs and the dotted line, which is nothing but IS1, gives you cosine of this, gives you the displacement power factor multiplied by I1, the RMS value of this current, and divided by IS, the RMS value of the total current, gives you the definition of power factor in case of nonlinear load. Therefore, we have written here that it is the displacement power factor multiplied by the fundamental component current divided by the total current. So this is how we will define the power factor in the case of nonlinear load. Okay. Now come to power factor improvement. For power factor improvement, there are two things. One thing is that you have to improve the displacement power factor, and the other thing is that you have to improve the distortion factor. Okay. Now, what is reactive power compensation? For reactive power compensation, you have to reduce the angle between the fundamental component of current and the voltage. Okay. So, if you improve this, the displacement power factor will improve. And the other part is I1 by IS. How will you remove I1 by IS? By removing the harmonics from the system. Okay. Therefore, you have to do two things at a time. The first one is that you have to improve the displacement power factor. Okay. That means you will have to reduce the angle between the fundamental component of current and the voltage. And the other thing is that you will have to reduce the distortion in the waveform, and by that way you will improve the ratio of I1 by IS. So for a good power factor, you will have to improve both the displacement power factor and I1 by IS. Now let us come to react power factor improvement. So for power factor improvement, there are two things. The first thing is that reactive power compensation. By reactive power compensation, you will reduce the angle between the fundamental component of current and the source voltage Vs. And the other thing is that you will have to remove the harmonics from the system by filtering them out. Okay. Now, there are methods for improving this. First, come to methods for reactive power compensation. The first method of reactive power compensation is thyristor switched capacitor. And wherever you have a thyristor switched capacitor, with that, you will have to use a thyristor controlled inductor also. Okay. Why we use thyristor controlled inductor with thyristor switched capacitor? I will tell you about this. And then we have static PWM static VAR compensator, or which is also known as PWM SVC, or this is known as instantaneous reactive power compensator with minimum energy storage elements. Okay, so these are the three basic methods for improving the power factor. Okay, now let us one by one discuss about them. The first one is your thyristor switched capacitor, or TSC. In short, we call it TSC. In thyristor switched capacitor, we have several capacitors connected to bidirectional connected thyristors. Okay, and depending upon your requirement, you go on switching the thyristors. You go on switching the capacitors one by one, depending upon the requirement. Okay, why do we have a large value of capacitor connected in parallel? Because if you switch on a capacitor, large value of capacitor, it will behave like a short circuit. Okay, therefore, instead of having a large value of AC capacitor, we will have several values of capacitor connected in parallel, and depending upon the requirement, we'll have to switch on the capacitors one by one. That is first C1, then C2, then C3, then C4, and then so on, and finally Cn, depending upon the requirement. And you have additional small inductor connected in series with the capacitor. This inductor has nothing to do with reactive power compensation. The purpose of this inductor, I am explaining you in the next figure, that what we do here, suppose this is your sinusoidal AC voltage. Okay, with respect to that, you will apply gate signals to thyristor T1. Thyristor T1 is your this thyristor support at the positive zero crossings. Okay, and similarly, you will apply gate pulses to thyristor T2 at the negative zero crossing. Therefore, what will happen, that this capacitor C1 will give you a fixed value of capacitance. Okay, and why do we turn it on using thyristor switches? Just to detect the zero crossings. Suppose you will switch on the capacitor somewhere here at the peak of the voltage. So in that case, there will be a situation like short circuit. A large current will flow depending upon the value of the capacitor. So we'll have to limit that current, and in order to do that, what we do, we turn on the capacitors at the zero crossings of the voltages so as to limit this large current. Additionally, we have also small values of inductors connected in series. This is because the fact that if you have not detected the capacity zero crossings of the voltages exactly, okay, in that case, that small amount of current will be limited by this additional inductor. So this inductor has nothing to do with the reactive power compensation. This is a small value of inductor. This is there so as to minimize the current if you have not detected the zero crossing of the voltage exactly. Okay. Now in this way, you will go on turning the capacitors one by one depending upon your requirement. Now suppose when you have turned on the nth capacitor, in that case, the power factor becomes leading. So in that case, what will happen? If the power factor becomes leading, in that case, your voltage will boost up and your receiving end voltage will be more than the sending end voltage because of this capacitive effect. And leading power factor is not desirable. So in that case, what will we do is that we limit this uh, capacitance value, or we nullify this capacitance value with a controlled inductor. Okay, therefore this capacitor is a switched capacitor. We call it thyristor switched capacitor. Okay, and this inductor is a controlled inductor. Okay, now what will happen here? Let us see in this diagram. Now this current, inductor current, will be, if we neglect the resistance of the inductor current will be lagging the voltage by 90 degree. Is not it? So whatever control you have, it starts from 90 degree up to 180 degree only. From 0 to 90 degree, you do not have any control. Okay. So what will happen? Suppose we have taken a value of alpha which is equal to 120 degree. Alpha cannot be made less than 90 degree because only at 90 degree the current is crossing zero crossing, and this thyristor cannot be turned on when the voltage is negative, because you know that for turning on the thyristor, it has to be forward biased, and also there must be a small current which you call as the latching current. This current through the thyristor must be greater than the latching current to turn it on. Okay, therefore from 0 to 90 degree we don't have any control. Okay, from beyond 90 degree only the thyristor can be controlled up to 180 degree. Now suppose we have taken a value of alpha is equal to 120 degree. So this IL, the current through the inductor, will be like this, shown by the solid line. Okay, and the fundamental component of the current will be shown by the dotted line. Okay, if we take a larger value of alpha, suppose 135 degree, in that case you see that the fundamental component has reduced. Okay, so if the fundamental component reduced, the effective value of inductance will also change. Okay, and this value of inductance, this will be somewhere maximum near alpha is equal to 90 degree, and this will be minimum somewhere alpha is equal to 180 degree. Okay, and using formula it can be written like this: if instantaneous voltage Vs is equal to root 2 Vs cos omega t, the RMS value of fundamental component to current flowing through the inductor L1 is given by IL1 is equal to Vs by pi omega L1 within bracket 2 pi minus 2 alpha plus sine 2 alpha, where alpha is from 90 degree up to 180 degree. Okay, now as the current through L1 is lagging the voltage Vs by 90 degree, alpha has no control from 0 up to 90 degree. Okay, and the effective value of inductance L1 is given by L effective is equal to omega IL1. And if you put this value of IL1 here, you will get L effective is equal to pi L1 divided by 2 pi minus 2 alpha plus sine 2 alpha, where alpha is between pi by 2 and pi. Okay, so in this equation, if you vary the value of alpha, okay, what is happening? The value of L effective, that is the effective value of inductance, will change. Now, what value of alpha you will take here? Depending upon the value of inductance that you want to nullify the additional value of capacitance which has been put in the circuit, and to avoid the leading power factor condition. Okay, therefore by changing the value of alpha, we'll have to we will have to obtain a value of L effective so as to nullify the additional value of the inductance. Therefore, what you have to do is that with thyristor switch capacitor as shown in this diagram, okay, when you go on switching the capacitors one by one, as soon as you turn on the nth capacitor, if the power factor is becoming leading, in that case, you will have to use this control inductor to nullify this additional capacitance and to make this power factor lagging but close to unity. Therefore, yes, pardon, yes, somebody is asking some question. Yes, yes. You have any question? It seems somebody is asking any questions. Do you have any questions? Okay, fine. Thank you. So with thyristor switch capacitor, you have to use thyristor. With thyristor switch capacitor, you have to use thyristor control inductor. Therefore, we have understood that the thyristor switch capacitor gives us fixed value of capacitors. Okay, and we use thyristor switches so as to detect the zero crossing, of the voltage, and to perform the switchings at the zero crossing of the voltage, and to avoid the short circuit condition or the large current which will flow into the circuit because of this capacitance. Okay, and then the thyristor control inductor gives you variable value of inductance, and you will have to use both the things together, okay, to take care of the power factor. Now, this equation has been derived. Therefore, let us use a scheme where you have thyristor switch capacitor and thyristor control inductor, and let us see how the power factor can be controlled in this scheme. You see this diagram. So in this diagram, this capacitor depicts the thyristor switched capacitor, and already I have told you that this gives you fixed value of capacitance. Okay, and then we have a thyristor control inductor which gives you variable value of inductance. Now, in this total scheme, let us see how the power factor can be controlled. Now you can say that leading VAR supplied is equal to Vs square divided by 1 by omega c. This is the leading VAR supplied, and the lagging VAR supplied is equal to what? It is equal to Vs into IL1, where IL1 is the fundamental component of current flowing through the inductor. The net VAR supplied will be equal to leading VAR supplied minus the lagging VAR supplied is equal to this. Now here, if I put the value of I1 from equation number 2, this will be like this. Okay, and the net VAR supplied is equal to you can write is equal to just a minute, is equal to Vs into Is sine phi. So if we equate these two equations, Vs Is sine phi is equal to this, so we'll get Is sine phi is equal to Vs within bracket omega c minus 2 pi minus 2 alpha plus sine 2 alpha divided by pi omega L. So using equation number 4, you will have to control the power factor. Therefore, what you have to do, so you have to measure the value of the reactive part of the current. Okay, and if you can measure the reactive part of the current, then this equation number 4 gives you the value of alpha for unity power factor condition. Okay, therefore what you have to do is that at the zero crossing of the voltage, you have to measure this current. Okay, and if you measure this current at the zero crossing of the voltage, this gives you the value of is sine phi, and from this value of the is sine phi, the equation number 4 will give you the value of alpha for the unity power factor condition. And if you turn on the thyristors at this particular value of alpha, this will give you a unity power factor condition. Okay, so this is how the reactive power is controlled using thyristor switched capacitors and thyristor control inductor. Okay, now what are the drawbacks of this scheme? The drawbacks of this scheme is, first, number one is that for limitations of TSC and TSI. As the VAR generated or absorbed in these schemes are directly proportional to the energy storing capability of capacitors and inductors, there is considerable increase in size of these elements when the VAR to be compensated is large. Therefore, if the VAR to be compensated is large, in that case, the value of L and C will be very, very large. Okay, and this is one of the major disadvantage of this scheme. And the other disadvantage of this scheme is that the TSC and TCI, that is thyristor switch capacitor and thyristor controller inductor schemes, has a major disadvantage that they generate additional current harmonics. How? You can see that, you can see here that depending upon the value of alpha. Okay, what is happening here? That if you take a large value of alpha, this current waveform is not sine wave. It is away from sine wave. And what do you mean by that? The fundamental component of current in it is reducing. That means the harmonic components are increasing. That means the thyristor switch inductor, which you are using for compensating the value of the additional value of the capacitance, this is injecting additional harmonics into the system. Okay, therefore, apart from the harmonics which are present in the system, you have used a thyristor switched capacitor with a control inductor, and the scheme is injecting additional harmonics into the system. And why you are using this? For displacement power factor. For you want to reduce the angle between the fundamental component of current and the voltage. But in that way, what you are doing, you are increasing the distortion in the system. And you have already defined the definition of power factor as it is displacement power factor multiplied by I1 divided by IS. And here what you are doing is that you are trying to improve the displacement power factor, but in that way what you are doing is that you are deteriorating I1 by IS. So this is one of the major limitations of thyristor switched capacitor and thyristor control inductor. Okay. Now, next we have a scheme which is known as PWM Static VAR Compensator. Okay, to overcome the limitations associated with TSC and TCI, pulse width modulated static VAR compensators have been proposed. The advent of gate controlled power semiconductor devices like GTOs, IGBTs, power MOSFETs, okay, has made it possible to manufacture static VAR compensators that can generate leading or lagging VAR with only one passive component, that is a capacitor for a voltage source converter and an inductor for a current source inverter. But in most of the cases, we prefer the voltage source converter because of the fact that in the case of current source converter or the current source inverter, the size of the inductor is very bulky. Okay, and to avoid that, we use voltage source converter where we require a DC capacitor, and large values of DC capacitors are easily available in higher values. Okay, and several topologies, techniques, and control strategies of PWM SVCs have been proposed in literature, and those are basically hysteresis band control, error triangulation control, dead bit control, sliding mode control. So many techniques have been proposed by different persons. Okay, Now let us see how this voltage source converter can supply the reactive power. Here in the diagram, we have a voltage source converter, and at the DC end, we have a capacitor. This capacitor is a pre-charged capacitor. Now, when the V compensation 1, okay, V compensation 1 is the fundamental component of V compensation, which has been generated here by controlling the switches S1 to S4. Okay, when V compensation 1 is greater than Vs, leading current with respect to the supply voltage Vs will be drawn, and the inverter supplies lagging VARs to the system. That means it will behave like a capacitor. This is what the capacitor does. Okay, it supplies lagging VARs to the system. When V compensation 1 is less than Vs, the inverter draws lagging current and it supplies leading VARs to the system. That means it can behave as an inductor also. And when V compensation 1 is equal to Vs, okay, no current will flow into or out of the system. Therefore, this voltage source inverter can behave like a capacitor or it can behave like an inductor, depending upon the value of V compensation 1 that you have obtained. And how you will get the V compensation 1? By proper selecting the switching sequences of the switches S1 to S4. Okay, you can have a V compensation 1 which can be more than Vs, or it can be less than Vs. If V compensation 1 is more than the supply voltage Vs, leading current will be drawn and the inverter supplies lagging voltage to the system. And when it is less than Vs, the inverter draws lagging current and it supplies leading voltage to the system. Okay. Now, the magnitude of Vc is kept higher than the amplitude of Vs. Okay. Why it is done that? Because you have to take a value of Vc because of which the voltage which is generated here is more than Vs. Okay. If this voltage is too small, there may be a situation where this V compensation 1 is always less than Vs. And if this V compensation 1 is always less than Vs, no current will flow from the inverter to the source side, and therefore the power factor cannot be improved in that case. Therefore, you have to take an initial value of Vs for which the voltage obtained here is more than the supply voltage, and because of which the current will flow from the inverter to the source side, and in that way the power factor can be improved. By suitable operation of switches, the voltage V compensation 1 having a fundamental compensation V compensation 1 is generated at the output of the inverter, and by that way it will behave like a capacitor and the power factor can be improved. Okay. Now, by controlling V compensation, the amount of reactive power can be controlled as the phase angle between I compensation and V compensation 1 is plus minus 90 degree. Either it is plus 90 degree or it is minus 90 degree. Either it is behaving like a capacitor when V compensation 1 is greater than Vs, or as an inductor when V compensation 1 is less than Vs. Okay. So, the phase angle between V compensation and I compensation is plus minus 90 degree. Okay. Real power is neither supplied nor absorbed by the DC source, VDC. Hence, the DC source can be replaced by a capacitor. The practical system will have some losses which are supplied from the source. The meaning of this is that the angle between the V compensation 1 and I compensation is either plus 90 degree or minus 90 degree. Okay. So when it is plus minus 90 degree or minus 90 degree, it will not take any real power from the system. Okay. And some amount of real power which is required to compensate the losses of the switches only will be taken from the system. Otherwise, it will not take any real power from the system. Okay. So by hence the DC source can be replaced by a capacitor, and practical system will have some losses which are supplied from the DC source, and these losses are not very significant. Okay. To limit the DC link voltage ripple within an acceptable margin, a fairly large capacitor is required for the single phase system. Okay, the increment in value of the DC link capacitor does not significantly affect the overall cost. However, the dynamic performance of the compensation is degraded. This is the meaning of that, is that even if this DC capacitor value is very large, okay, this DC capacitor will be an electrolytic capacitor, and the electrolytic capacitors are not very costly capacitor. You can use an electrolytic capacitor here. The only difference will be that dynamic response of the system will be degraded, okay, because the time constant of the circuit will be large in that case. Okay, so this is how a PWM VAR compensator can be used for reactive power compensation. Okay, and there are certain standards and guidelines for harmonic currents and voltages, okay, which are EN 50006, okay, then IEC norm 5553, then West German standards VDE 0838, okay, then IEEE guide for harmonic control and reactive power compensation, okay, IEEE 519 1992, okay. So these are the guidelines for harmonics by different agencies, and in most of the cases we use this IEEE 519 1992, and this says that if the distortion in the current is within 5%, we will assume the current to be sine wave, and if the distortion is THD is more than 5%, in that case you are required to filter it out, or else you will be penalized for that. Okay, so you will have to take care of the harmonics of the system. You are using nonlinear load in your premises, okay, and because of which the power factor is deteriorating. Now you are responsible for that. You will have to remove, if you are generating the harmonics, you will have to remove the harmonics from the system, okay, and your TSD should be within 5%. Otherwise, what will happen? Because your harmonics, the other people who are connected to that system through the common point of coupling, their voltage will not be sinusoidal, and for which they are not responsible, for which somebody else is responsible, who in whose premises there are lot many nonlinear loads. Okay, therefore if you are generating the harmonics, you will have to remove the harmonics from the system, or else you will be penalized for that. Okay, so there are different standards of harmonics, okay, given by different agencies, and we'll have to take care of that, or else we will be penalized for that if the TSD is beyond certain limits. Now, for harmonic filtering, there are two types of schemes. The first scheme is known as shunt passive filter, and the second one is known as active power filter. Now, what is a shunt passive filter? Shunt passive filter have traditionally been used to absorb harmonics generated by nonlinear loads. They use LC resonating circuit offering negligible impedance at the tuned frequency. Okay, the low impedance path allows the harmonic currents to flow through them. Shunt passive filters provide harmonic filtering at the load end, at the source of harmonics, and hence reduce the voltage distortion at the load terminals. The meaning of this is that if you want to remove the third harmonic, okay, so you tune your LC at the third harmonic frequency, okay, and when it is tuned at the third harmonic frequency, the third harmonic frequency current will find a low impedance path through it. Okay, current always flow through the low impedance path, and since your LC resonating circuit is tuned at the third harmonic frequency, so the third harmonic frequency current will flow through that, and the system will be relieved of the third harmonic frequency. If it is tuned at the fifth harmonic, okay, so the fifth harmonic frequency current will find a low impedance path through it, and the system will be relieved of the fifth harmonic frequency. Therefore, depending upon your requirement, depending upon your harmonics, you will have to tune different shunt passive filters at the dominant harmonic frequencies. Okay, if it is a single phase system, the most dominant harmonic is the third harmonic. Okay, then we have the fifth harmonic, then we have the seventh harmonic, like that. If it is a three phase system, the most dominant harmonic will be the fifth harmonic, then we have the seventh harmonic, and like that. Okay, So we will have to tune different set of shunt passive filter tuned at different harmonic frequencies to get rid of the harmonics. Now, when you use so many things together, there are associated problems also. Now, what are the limitations of shunt passive filters? The limitations of shunt passive filters are for filtering several harmonics, different shunt passive filters are required because one passive filter can filter out one harmonic frequency current effectively. Okay. The next one is that the source impedance strongly influences the compensation characteristics of passive filters or shunt passive filters. For nonlinear nodes connected to systems having low supply side inductance, it is difficult to design passive filters with sharp tuning. Okay. Now, if the source inductance is very small, which is known as stiff bus. So okay, so in that case, it will be difficult to have a impedance difference of the some shunt passive filter and the source. Okay, and therefore some of the harmonics current will flow through the source also. And for such system, it becomes difficult to design a shunt passive filter. And for designing a shunt passive filter, there are several things which we'll have to take into account. First of them is that what is the quality factor of the shunt passive filter? Okay, and for a good tuning, the quality factor should be somewhere near 20 or 25 or more than that. If your quality factor is too less, in that case, if the quality factor is order of say 5, 6 or 10, in that case, your resonance curve will be flat curve. And therefore, in that case, the shunt passive filter will not work effectively. Okay. So therefore, your shunt passive filter should have a optimum value of Q. Okay. Then we have they are highly susceptible to undesirable series and parallel resonance with the source and the load. Now, what happens? The source has certain inductance. The load has a certain inductance also. Okay, and because of which there's an effect which is known as parallel resonance. And because of this parallel resonance, what happens? The shunt passive filters are detuned. And if the shunt passive filters are detuned, that means you have tuned it at a third harmonic frequency, or you have tuned at a fifth harmonic frequency. And because of this effect of parallel resonance, series and parallel resonance, it is effectively tuned at 3.1 or 5.1 like that. Okay, therefore, it is not exactly tuned. And to take into account of this, what is happens initially we does not tune we do not tune it at exactly third harmonic or fifth harmonic. Rather, we tune it at 2.9 or 4.9 like that, so that after taking into account the effects of the series and parallel resonance, effectively it is tuned to third harmonic and fifth harmonic. Therefore, the tuning of the exact tuning of the shunt passive filter is very difficult, or it is not possible because of the effect of the series and parallel resonance. And when the harmonic component currents increase, the passive filters are overloaded. Okay, how they are overloaded? Because if the amount of nonlinearity in the system goes on increasing, in that case, what will happen? The third harmonic, fifth harmonic, those will also be increased, and you will have to design your filters accordingly. Otherwise, the filters will be overloaded. So these are the major limitations of shunt passive filters. Okay. First of all, you require a large number of shunt passive filters tuned in dominant harmonic frequency. Then we have the effect of source inductance. Okay. Then we have we have the the effect of overloading of the shunt passive filters because of the increase in level of the harmonic currents and so on. Okay. Then we have the active power filters. What is the active power filter? When PWM converters are used for harmonic filtering, in addition to reactive power compensation, they are known as active power filters. Therefore, here, initially we described a converter and we said that this converter is used for reactive power compensation. Okay, now this converter can be used for reactive power compensation along with harmonic compensation, and in that case it is known as active power filter. So the active power filter is nothing but it is just the PWM converter or instantaneous VAR compensator, but it is in that case it is used for a reactive power compensation as well as the harmonic filtering. Okay, now therefore the control of the active power filter is a thing which we'll have to take into account. Basically there are two types of control. The first one is known as indirect current controlled active power filter, and the second one is known as controlled current active power filter. Okay, I will discuss it about later on. Okay, in indirect current control active power filter, which is very simple, the active filter is indirect current control and is based on voltage source inverter. The voltage source inverter is controlled by two loops, the voltage control loop and the current control loop. The voltage control loop regulates the DC link capacitor voltage. The current control loop shapes the source current such that the source current is in shape with and of the same shape as the input voltage. Okay, and the reference current for harmonic filtering and reactive power compensation is generated from the DC link capacitor voltage. Let us explain it with the help of a diagram, block diagram. Okay, now here what you have a nonlinear load. Okay, and you have used a voltage source converter here. Okay, to compensate the reactive power as well as the harmonics. Now there is a capacitor here. Okay, now, first of all, what you have to do is that you have to use a low pass filter. Okay. And after that, after low pass filter, you got a VC here. This VC has to be compared with a reference VC, and this difference has to be sent to a PI controller or any type of controller. Okay. And then the difference K is to be multiplied with the type of sinusoidal waveform, or which is known as the reference current. Okay, and then it is sent to the controller, and finally the current controller uh, generates the firing pulses for the switches of the voltage source converter, and this generates such pulses for which the converter gives you the voltage source inverter gives you the required amount of reactive power and the required amount of harmonics so as to compensate the uh, displacement power factor as well as the distortion in the system. Okay, now here you can use different types of controllers. Okay, it can be a fuzzy controller also, it can be an ANN based controller also. Okay, so as to improve the performance of this controller. So this is a very simple scheme. Using this type of control scheme, you can do reactive power compensation as well as harmonic filtering. Okay, this can be used. There are different types of control schemes about which I will discuss later on. Before that, I want to discuss another thing which is very important here. Large value AC capacitor for harmonic filtering and reactive power compensation. Okay, now what is this? Usually, practically, we don't have large value AC capacitor. Why we don't have large value AC capacitor? Because we don't require large value of AC capacitor. Because already I have told you that in the reactive power compensation scheme, we use several values of capacitors. Why we use several values of capacitor? Because if we use a large value of capacitor, initially the current will be very large. Okay, so we use several values of small capacitor which are put into the circuit one by one depending upon the requirement. Now, if you have a large value of AC capacitor, then what will happen? So for that, we will have to obtain a large value of AC capacitor. Now let us see, can we obtain a large value of AC capacitors from DC capacitors? Because the DC capacitors are available in large values, like electrolytic capacitor. Although the electrolytic capacitor has substantially large equivalent series resistance, but these capacitors are very cheap, okay? And these are available in large values like 2000 microfarad, you will get in 3000 microfarad, 4000 microfarad, okay, at supply voltages and above. Okay, so let us see if it is possible to obtain a large value of AC capacitor from the DC capacitors. Is it possible? So let us see. Now, for that, I have proposed a circuit here. You look this circuit first. Now, in this circuit, you can see that there are two DC capacitors, C1, C2. There are two diodes, D1, D2, and there are two switches, S1 and S2. These switches can be IGBTs. This can be power MOSFET. Okay. Now, here you see what happens here. Initially, this operation can be explained by using this figure number 9. You see here, there are in the initial mode 1, okay, what happens? C1 and D1 is conducting, okay. So when C1 and D1 is conducting, what is happening? You see, during first quarter cycle, current flows through C1 and D1, okay. The capacitor C1 charges to peak supply voltage at the end of this interval at T1. That means I want to say that at the end of this interval, the capacitor is charged to this maximum voltage here. Okay. At the end of this, during the first quarter cycle, current flows through C1 and D1. The capacitor C1 charges to peak supply voltage at the end of this interval at T1. The capacitor C2, so when it is conducting, you can see that when C1 and D1 is conducting, okay, now there will be some amount of voltage drop across the diode D1. And what is the voltage drop across diode D1? It is about 1 volt or less than 1 volt. So this much of voltage is appearing across capacitor C2 in the reverse direction. Now, an electrolytic capacitor of 400 volt or 500 volt can withstand a reverse voltage of the order of 3 to 4 volts. Okay, and this voltage, the voltage drop across the diode, which is of the order of 1 volt or less than 1 volt, is very less than 3 to 4 volts. So even if this voltage is appearing across the capacitor C2 in the reverse direction, that will not harm the capacitor. Is it all right? And then what is happening? The capacitor C2 experiences a small reverse voltage equal to the forward voltage drop of diode T1. The small reverse voltage is well within the specified negative voltage limit of DC capacitor C2. This is important since DC capacitors have very small negative voltage limit, which is 1 to 2 volt. Okay, and gate pulse is applied to S1. Gate pulse is applied to S1 at the beginning of this mode. Okay, but this S1 will only be turned on at T1. Okay, this is done to avoid any turning on or on of the switch S1. And when this S1 is turned on, what will happen? This capacitor C1, which was charged to the maximum of the supply voltage, now starts discharging. Okay, and by the end of this mode, at T2, the capacitor is completely discharged. Therefore, what is happening here in the mode 1? Okay, what is happening? C1 and D1 is conducting. Okay, and at the end of this mode at T1, this capacitor is charged to the maximum voltage, which is equal to the supply voltage Vs. Okay, and now we need to discharge this capacitor. Now, for discharging this capacitor, what we are doing is that we are turning on switch S1. And when switch S1 is turned on, this capacitor discharged through S1, and at the end of the discharge, okay, at T2, this capacitor voltage becomes 0. Okay. Similarly, in the negative half cycle in mode 3, what is happening? C2 and D2 are conducting. Okay. And when C2 and D2 are conducting, at this end of this mode at T3, this capacitor C2 is charged to the maximum of the supply voltage in the reverse direction. Now what we are doing here, we are turning on switch S2 at the beginning of mode 4 to discharge this capacitor voltage of C2, and at the end of this mode, that is at the end of at T4, this capacitor is fully discharged. So in this way, using two capacitors C1 and C2, two diodes D1 and D2, and two switches S1 and S2, what we are doing is that we are getting the behavior of an AC capacitor. Okay, and for that we are using two DC capacitor, two switches S1, S2, and two diodes D1 and D2. I am again repeating this operation of this circuit. This operation of this circuit can be divided into four modes. In mode 1, you can see that C1 and D1 are conducting, and when C1 and D1 are conducting, okay, you see that at the end of this mode here, okay, the capacitor voltage becomes equal to the supply voltage, okay, and at this point, that is at the beginning of mode 2, that is at T1, okay, you turn on switch S1, and when you turn on switch S1, this capacitor will start discharging, okay, and at the end of this mode T2, what is happening? The capacitor is completely discharged. And in the beginning of mode 3, what is happening? C2 and D2 starts conducting, and when C2 and D2 are conducting, what is happening? This capacitor voltage is going to the negative side, and here it becomes equal to minus Vs. And when this becomes equal to minus Vs, you turn on S2 to discharge this capacitor voltage, and at the end of this mode, that is at T4, this capacitor C2 is completely discharged. Therefore, you are using capacitor switch S1 to discharge this capacitor C1, and we are using switch S2 to discharge this capacitor C2. So in this way, by using two additional switches and two diodes with capacitor C1 and C2, we are obtaining the performance of the AC capacitor. Okay, so this has been explained here. I'm not repeating here. Now, one of the things that I've already told you is that to perform the switching exactly at the beginning of T2, what you have to do is that you have to apply the gate signal a bit earlier, okay? So that as soon as you reach this point T1, okay, the switch S1 is turned on. Similarly, in case of S2, you have to apply the gate signal before the start of this mode, so that as soon as this mode starts, this switch S2 starts, okay, without any delay. Now, with this capacitor, let us see what we can do. So, we have obtained a large value AC capacitor using C1, C2, D1, D2, and S1, S2. Okay, and this capacitor is denoted by C. Can you hear me, all of you? Am I audible?
Yes, sir.
Yes,
Audible.
sir.
Okay,
Yes,
fine,
sir.
fine. Okay. Now,
Yes, sir.
now you see, using two electrolytic capacitor, DC capacitor C1, C2, two diodes D1, D2, two switches S1, S2, we have obtained an AC capacitor C. Okay. With this C, we have put an inductance L1 here, and this is a parallel resonance circuit here. This parallel resonance circuit is the combination of C, which we have obtained using C1, C2, D1, D2, and S1, S2. So using these things, we have obtained an AC capacitor C. With this C, this L1, where R1 is the resistance of the circuit of inductance and capacitor, including these resistances, this resistance becomes R1. Okay, this is a parallel resonance circuit, and with this we have another series resonance circuit, which is formed by capacitor C and inductor L2. Okay, and this resistance R2 is the resistance of the inductor. Now here, the impedance will be given by this equation number 1. Okay, and in this equation, if this circuit is in the fundamental frequency, so L1C is equal to 1 by omega naught square. So this ZF j omega naught becomes equal to infinity for this case. Okay, so if this is infinity, that means for the harmonic frequency current, it will provide a very good filtering, whereas L1 L2 divided by L1 plus N2 to C is equal to this. So for for the fundamental frequency, it will not, it will not permitting the fundamental frequency to flow through it, because the impedance is very high, and for the nth harmonic, it is providing very good filtering. again I'm repeating, the impedance of this circuit, okay, is given by equation number 1. In this equation, L1C is equal to 1 by omega naught square. That means this parallel resonant circuit is oscillating at the fundamental frequency. So ZF j omega naught is equal to infinity. Therefore, for the fundamental frequency, this is providing very high impedance. Therefore, it will not allow the fundamental frequency current to flow through it. Whereas for the nth harmonic frequency, this impedance is 0. Therefore, it is allowing all the harmonic frequency current to flow through it. Okay, let us understand it by this diagram also. The frequency response loss of the quasi-passive filter. I have termed it as quasi-passive filter. Okay, quasi-passive filter. This is different from the shunt passive filter. Okay, now I have taken different values of C. Now in trace 1, 2, 3, the capacity, this is trace 1, this is 2, this is 3. The capacitance value is 1000 microfarad, 1500 microfarad, and 2000 microfarad. And accordingly, the values of inductor L2 is calculated when the QPF is tuned to the third harmonic frequency. And these are the things that you have obtained, shown by 1, 2, and 3. Now, 4, 5, 6, okay, where capacitance value is 500 microfarad, 750 microfarad, and 1000 microfarad when the QPF is turned at the fifth harmonic frequency. So it is 4, 5, 6. Okay, and shunt passive filter tuned at third harmonic frequency. This is the normal shunt passive filter tuned at the third harmonic frequency by trace C. Okay, where the capacitance value is 50 microfarad and value is 22.5 millihenry and R value is 0.1. Okay, and the frequency response plot of the source impedance for LS value of 2.5 millihenry and RS value of this. So this is the source impedance shows, and you show here as you go on increasing the value of the capacitance, it is ultimately providing you better filtering effect. If the distance is more, okay, it is giving you better filtering effect. So this is for the third harmonic frequency and this is for the fifth harmonic frequency. Therefore, it is evident that larger the value of capacitance, better is the filtering effect. Okay, the meaning of this that larger this value of the capacitance, better is the filtering effect. But at the same time, if the capacitance value is very large, that means you have to take large values of C1 and C2 here. Therefore, the circulating current, the fundamental circulating current in this parallel resonance circuit is very large. Okay. Therefore, your capacitor and inductor has to be rated accordingly. You have to handle a large value of current. Okay. That is the disadvantage of that. So you have to make a compromise between that. What value of capacitance that you require, whether it is 500 microfarad that you require or you require 1000 microfarad, and accordingly you have to design your circuit. Remember, if the value of the capacitor is very large, in that case the current flowing through the parallel resonant circuit is very large and you will have to handle the large value of the current. Okay, the current flowing through the capacitor and the current flowing through the inductor is very large in that case. So that is one of the disadvantages of this scheme. Now this has been simulated for different cases. Suppose in the first case, it has been simulated for a diode rectifier feeding RC load where the capacitance value is made very large of the order of say 1000 microfarad. Okay, and we have intentionally made the capacitance very large because when you make this capacitance value very large, the harmonics here will be very large. Okay, and let us see whether this system is working for that large value of harmonics or not. When you design a system, you would like to test it for the worst case. Okay, and for this worst case, we have taken a diode rectifier feeding RC load. Okay, and where the capacitance value is intentionally made very large of the order of 1000 microfarad, and let us see what is happening in the circuit. Okay, now IRL is the load current. IRL is the load current. This is the load current here. We are seeing the load current here. So here you can see that lot of harmonics are present in the source current. Okay, and here we are performing the switching somewhere at say 400 millisecond. We are performing the switching. Okay, so you can see that the harmonics in the load current is very large. Whereas if you see the source current, the harmonics in the source current is very, very less. It is close to sinusoidal. V1 is the voltage here. V1 is the voltage here, okay? And we are seeing the current, okay? So you can see here that the current ILS, ILS is the current through the source. This current contains very little harmonics, okay? And it is very close to sinusoidal, okay? And here, if you see the current through IC1 and IC2, you can see these are the current through IC1 and IC2, okay? And you have to see that there is no spikes here, okay? Spikes will come only when there is improper switching, okay? You have to take care of these spikes, which may come into the system while turning on the switches. And if the spikes are very large, it will damage your switches. So you will have to take care of the spikes. Okay. Now, if you say V2 minus V3 and V3 minus V4, what is V2 minus V3? V2 minus V3 is the voltage across capacitor C1, and V3 minus V4 is the voltage across capacitor C2. Okay, now you can see that V2 minus V3 and V3 minus V4 together it becomes sinusoidal. Okay, this gives you the positive half, V2 minus V3 gives you the positive half, and V3 minus V4 gives you the negative half. And these together, that means the voltage between V2 and V4, V2 and V4, which is V2 minus V3 and V3 minus V4. So this becomes a sinusoidal voltage, okay? And the current flowing through the parallel resonance circuit is perfectly sinusoidal. You can see that I1 is perfectly sinusoidal, okay? And the current flowing through the filter, okay, that is current flowing through IL2 is the filter. You can see it contains only the harmonic components, and very little fundamental component is there, okay. And if we can neglect the resistance of the capacitors and the inductors, the fundamental component will be almost zero, okay. So let us see the harmonic spectrum of this, okay. If you see the harmonic spectrum of this, things will be more clear to you. So let us see in the next slide, let us see the harmonic component of this, okay. So in the simulated waveforms, we have seen the IRL, which contains a lot of harmonics, source current ILS, along with the voltage at node 1 V1. Then have seen the current through the capacitors IC1 and IC2, capacitors voltages V2 minus V3 and V3 minus V4, and the current in the parallel resonance circuit IL1, and the current through the third harmonic filter IL2. That means here we have tuned this shunt passive filter at the third harmonic frequency, and only using one harmonic frequency filter, we are trying to filter out all the harmonics, and whether it is possible or not, that we are investigating, okay. So you can see that in the load current, apart from the fundamental component, third harmonic component is there, fifth harmonic component is there, all the harmonics are there, okay. So its TSW very, very high. Whereas in ILS, you can see that it is almost sinusoidal, okay. The third harmonic is not at all there, the fifth harmonic is not there, seventh harmonic is not there. It is almost sinusoidal because only the fundamental component is there. So is the case with V2, okay. You can see that V2 is perfectly sinusoidal, very little fifth harmonic component is here. IL1, you can see that IL1, the current through the parallel resonance circuit IL1, it is perfectly sinusoidal, very little harmonic component is there here, okay. And if you see the current flowing through the shunt passive filter, you can see that very little fundamental component is there, and all harmonics are there, okay. This is the third harmonic, then we have the fifth harmonic, then we have the seventh harmonic, like that, okay. This much of fundamental component current also you can minimize by reducing the resistance of this inductor and this inductor, okay. So if you can neglect this resistance of the inductor, this will contain no fundamental component. But practically, you know that the inductor will have some resistance, the capacitor will have some resistance. So practically, you cannot neglect this resistance totally. Therefore, we have taken small value of resistance, okay. And the effect is that very little fundamental component will through it. Otherwise, all harmonic component will flow through it. Therefore, we can conclude that if we have a very large AC capacitor, okay, in the shunt passive filter, tuned at the dominant harmonic frequency. For the third single phase case, the third harmonic component is the most dominant harmonics. So we have tuned it at the third harmonic frequency, and we are showing that all harmonic frequencies are eliminated. You can see that in the IRL, apart from the fundamental component, all harmonic components are there. Okay, and we are using only the one shunt passive filter tuned at the dominant harmonic frequency, and we are showing that all harmonics are absent. Okay, so this is one of the things, that if you have a large value of AC capacitor in the shunt passive filter, it can filter out all harmonic frequency current if the filter is tuned at the dominant harmonic frequency, and you don't require many shunt passive filters tuned at the dominant harmonic frequencies to take care of the harmonics. Okay, now this can be done for another case also, where diode rectifier feeding RL load. Okay, this is a practical load because diode rectifier RC load is not a practical load. Okay, so in this case the TSD will be even lesser than that. This case also you can see that this is working fine. Okay, you can see that here this is IRL, this is ILS, this is V2, this is IL1, and this is IL2. So with RC load and RL load, in both the cases, it is working satisfactorily. There is no problem with the quasi-passive filter that has been designed. It is working fine for diode rectifier feeding RC load and diode rectifier feeding RL load. Okay, in both the cases, it is working perfectly all right. Okay, now we have taken a typical harmonics case in a single phase input current waveform with no line filtering. This third harmonic frequency is made as high as 73.2%. The fifth harmonic is 36.6%. The seventh is 8.1. This is very large. With these harmonic content, if you calculate the TSD will be of the order of 85%. Okay, 80 to 85%. In practical cases, the TSD is not that high, but intentionally we have made the TSD high to test the performance of the filter. And this example has been taken from the Ned Mohan's book, The Typical Harmonics in a Single Phase Input Current Waveform with No Line Filtering. And we are testing the performance of the quasi-passive filter that has been designed. Okay. Now, if we take the value of C1 and C2 to say 1500 microfarad, okay, in that case, the current TSD is of the order of 7%, okay, and the voltage TSD is of the order of 5.24%, okay. If we increase the value of capacitance C1 and C2 to say 2000 microfarad, in that case, the current TSD reduces to 5.5% and the voltage TSD reduces to 4.1%. Okay. If you further increase it, you can see that the current TSD and voltage TSD are further decreasing. Okay. And if C1 and C2 are 500 microfarad with an additional third harmonic filter, so in that case, you require an even smaller value of capacitor. Okay, a value of capacitor of the order of 500 microfarad gives you a TSD of the current TSD of the order of 4.4% and a voltage TSD of the order of 2.48%. Therefore, with the worst case also, this quasi-passive filter is working satisfactorily. Okay, even with a capacitor value of 500 microfarad with an additional third harmonic filter, okay, conventional third harmonic filter, okay, with the TSD of the order of very high, of the order of 80 to 85%, the TSD can be reduced to less than 5%. Okay, so this is one of the things that I wanted to tell you, that if we use a very large value of AC capacitor in the shunt passive filter, all the harmonic frequency current can be filtered out with one set of shunt passive filter tuned at the dominant harmonic frequency, and this filter has been named as quasi-passive filter. Okay, now let us see whether this circuit can be used for reactive power compensation also, because using the quasi-passive filter we have eliminated all the harmonics. Now let us see let us investigate its performance for reactive power compensation also, in addition to the harmonic filtering. Okay. Now, we have modified the static VAR compensator a little bit, okay? And here we are using the large value AC capacitor. Initially, I told you a static VAR compensation, which was somewhat like this, but slightly different than this, okay? So here what you are using is that you are using a large value AC capacitor C along with an inductor L2, okay? And this C and L2 inductor is tuned at the dominant harmonic frequency. And additionally, you have a inductor L1. Why you are using this inductor L1? You are using this L1 to detune this circuit. Okay, some amount of fundamental component in the earlier version, we blocked the fundamental component totally. Okay, in this version, we block the fundamental component totally. In this case, we block the fundamental component totally. Okay, whereas in this version, what we are doing, we are permitting some amount of fundamental component to flow. Okay, depending upon the displacement power factor, depending upon the fundamental component it require to compensate the reactive power, that much is allowed to flow through the circuit. Okay, now let us see the operation of this circuit. Okay, again in this case also IN1 is lagging the voltage by 90°. So you have a control from 90° to 180° only. Now the instantaneous source voltage can be represented at Vs is equal to root 2 Vs cos omega t. The RMS value of fundamental component of current flowing through the inductor L1 is given by this equation. This is a very standard equation. Okay, where alpha is the thyristor delay angle. As the current through L1 is lagging the voltage Vs by 90°, alpha has no control from 0 up to 90°. Okay, so whatever control you have control from 90 to 180° only. From 0 to 90°, you have no control over the alpha. Okay, because you cannot turn on the switches T1 and T2 before 90°, because the current is in the negative direction in that case. Okay, so the effective value of inductance can be given as Vs divided by omega I L1, so which is equal to pi L1 divided by 2 pi minus 2 alpha plus sine 2 alpha, where alpha varies from 90° up to 180°. Okay, so the effective susceptance of L1 is given by B effective is equal to 1 by omega L effective, and this is given by this equation. The leading VAR supplied by MSVC, that is modified static VAR compensator, is given by Vs squared by 1 by omega C minus omega L2. Lagging VAR supplied by MSVC is what? Is equal to Vs into IL1. Therefore, the net VAR supplied by MSVC is equal to QMSVC is equal to this minus this, as given in equation 7. Now, what we are doing is that larger the capacitor size, higher will be value of QMSVC, which results into higher power rating of MSVC. The lagging VAR of the system load is given by QL is equal to Vs into Is into sine phi, where phi is the power factor angle. The lagging VAR of the system QL and leading VAR supplied by MSVC are equal at unity power factor condition. Okay, so equating equation number 7, okay, and equation number 8 as shown here, okay, 7 and 8, okay, we get IL1 is equal to Vs divided by this minus Is sine phi, okay, as given in equation number 9. Okay, substituting IL1 from 2 into 9. Now IL1 we have written in equation number 2, okay, and this is put into equation number 9. So if you put this here, you will get this equation. So whatever control that you will have to do is using equation number 10 for reactive power compensation. Okay, now you can see that for fixed supply voltage Vs and fixed value of C, L1 and L2. Okay, C is your this capacitor value, C is your this capacitor value, and this L1 and L2. So you can write here is that, okay, for fixed supply voltage Vs and for fixed value of C, L1 and L2, equation 10 relates reactive current Is sine phi and firing an alpha. Thus, reactive current can be controlled by controlling alpha of the thyristors. So what here is basically is doing is that you are measuring the value of IS sin phi. Okay, and this equation gives you a value of alpha for which this will be working at unity power factor condition. Okay, and therefore, if you know the value of Is sin phi, you have to calculate the value of alpha from here. And then if the thyristor is fired at that alpha, okay, it will take care of the reactive part of the current. Therefore, using this large value of AC capacitor, you can do reactive power compensation, and at the same time, you can also eliminate harmonics from the system. Therefore, you can improve the power factor using this large value AC capacitor. Okay, and the advantage of the system is that, okay, with one set of MSVC tuned at the dominant harmonic frequency, you are filtering out all the harmonic frequency current. And at the same time, you are also supplying the reactive power required to improve the displacement power factor. Okay, so the original scheme, which was thyristor switch capacitor and thyristor control inductor, in there we have used a large value AC capacitor, and using the same scheme, we are saying that with one set of shunt passive filter tuned at the dominant harmonic frequency, we are filtering out all the harmonics, and at the same time, using the same scheme, also we are removing the reactive, we are supplying the reactive current lead required by the system to compensate the compensate and make the displacement power factor close to unity. Okay, and this has been simulated here using a simulation diagram. How much time is left, Ambaresh? How much time is left? It is 3:51. Okay, so
Yes,
I within 10 minutes I am completing. Okay,
yes, yes,
and
yes, yes,
then for I will give you time to ask questions. Okay, okay.
yes,
So
yes,
this
sir.
has been simulated here. Okay, using the simulation scheme, you can see that this has been simulated using PSpice software. You can see that the power factor becomes unity, the voltage and current are in phase, and here this is the current because this is combination of linear and nonlinear load. Okay, this is nonlinear load and this part is linear load. Using this combination, using this combination, we have made the TSD. The TSD cannot be made very high because we have another linear load also. Okay, and this is the current, and this has been compensated here using this scheme. So you can see that simulated waveform for MSBC, the load current IRL, the source current ILS, okay, the capacitor current IC1 and IC2. You'll have to take care of the spikes, okay, and D, the capacitor voltage V2 minus V3, which is a perfect sine wave, okay. So these are the harmonics there. IR will contain harmonics, okay, whereas in ILS you don't have harmonics. Okay, now this is how it can be done experimentally. Okay, so here in experimentally, this is from G1 K1 and G2 K2, you will get the firing pulses for the thyristors, and this from these firing pulses you will have to fire the thyristors T1 and T2. Okay, so what are you doing here? You are sensing the current, okay, first, and then you are using an A to D converter, and using this A to D converter, what you're doing is that you are converting that analog value into digital value. So what are you doing that initially at this point, you are seeing the current IS sin phi, okay? And then you are converting it into digital form. You are converting into digital form. And in the processor, what the processor is doing, this processor is giving you the necessary firing angle of the thyristors to make this power factor unity. Okay, so which has been done here, and here you have used a PLL. This PLL is used here to take care of any change in frequency. Okay, because the system frequency is constantly changing, so you have to use a phase loop here to take care of the harmonics, and thereby I can show you the practical result. This practical result has been taken long back. I can see you the practical result here. Okay, you see the source voltage and source current, and experimental source current harmonic spectrum without connecting MSVC. There is harmonics in there, and when you connect the MSVC, you can see the source current is practically sinusoidal, and there is no harmonics present here. Okay, so the conclusion is that this modified static VAR compensator MSB has been proposed for reactive power compensation using a large value AC capacitor. The large value AC capacitor has been realized using two large DC capacitors and power semiconductor devices. Simulation and experiment results establish that with a large value of capacitor, okay, in the MSVC, the TSD of the source current and voltage at PCC can be reduced to less than 5% by the proposed MSVC having only one set of shunt passive filter tuned at third harmonic frequency. This is a major advantage of MSVC over conventional SVCs, in which different sets of shunt passive filters tuned at different harmonic frequencies are required for filtering different harmonic frequency current. Since the MSVC does not require high performance complex inverters as requires in conventional APFs. In conventional APFs requires inverters of high performance. It can be used in high power applications, okay, than conventional APFs. Okay, so this is what about your the quasi-passive filter or modified static VAR compensator, which can be used for reactive power compensation and harmonic filtering. Similarly, you can have a study of active power filters also. Okay, in active power filters also, I'm just showing you the results only. We can use hysteresis band control, okay, or any type of control suitable to you. These are the equations derived here. Okay, I'm showing you the results here. Final results. This has been done for single phase case and three phase case both. Okay, you can see here is that IRL is equal to 92%, whereas ILS is equal to only 1%. Okay, for RC load, for RL load, it is 37% and it is 0.8%, very less. And for three phase case, where the TSD is not very high, it is 20% and it has reduced to 0.34% choosing the active power filter, indirect current control active power filter. I'm showing you the results only because we have less time. So here you can do it by using active power filter, but in active power filter you require a lot of complex circuitry. Okay, whereas here we practically don't require any control circuitry. Without using any control complex circuitry, okay, you can do both reactive power compensation and harmonic filtering simultaneously using this modified static VAR compensator, where you are using a very large value AC capacitor. Okay, and since large value of AC capacitor is not available, what we have done, we have designed a large value AC capacitor using two DC capacitors. Okay, two DC capacitor, two switches S1, S2, and two diodes D1 and D2. Okay, so we realized a large value AC capacitor, and then using that large value AC capacitor, we established that all the harmonics can be eliminated if the shunt passive filter is tuned at the dominant harmonic frequency. And at the same time, we can also provide reactive power to the line, and thereby we can improve the displacement power factor also. And this is how the you can finally improve the power factor, or you can say the term power quality. These days power quality terms is very frequently used. Okay, you can improve the power quality using harmonic filtering and reactive power compensation using a large value AC capacitor. Okay, now the time is, I think, over, and if you have any questions, you may ask me questions. Okay, is it okay, Ambarish?
Yes, sir. Yes, sir. So if any participant having any question, then you can ask. Anyone? I think some of them asking in the chat box. How to derive the transfer function for impedance frequency response? And, sir, you are muted, sir.
Yes, yes, yes.
So somebody asking how to derive the transfer function for the impedance frequency response.
Let no, just a minute. I'm coming back to the screen. Can you see this? It has been shared. It has been shared.
Yes, sir. Yes, sir. It is
Okay.
coming.
We don't require to do that. We don't require to do that. You see here, what we require here is that only thing is that this is separate from the active power filter. That's why I said you don't require any control here. You see here, what you have to do is that you have to write this equation. This is very simple to write. Okay, you can write this expression for impedance, and from this impedance expression, if L1C is equal to 1 by omega naught square, this is for the fundamental frequency current. This is providing you infinite impedance. Okay, and for nth harmonic, it is providing 0. Okay, we don't require to do that actually. Okay, that is my answer. Okay,
Okay.
you don't require any such type of thing here, which is required in active power filter. That's why I said that the control is very, very simple here. Okay.
Yes.
Okay,
So,
then
is anybody else having any question? No. So, I think that there is no question. So, thank you very much, sir,
okay, okay,
for
thank you very
giving
much.
us
Thank
the details of this harmonics and reactive power to all the participants. So, thank you from my side and from the side of the participants.
okay, 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 okay. Thank you very much. Thank you very much. Okay.
Okay.
Now I'm disconnecting.
Yes,
Okay.
sir. Thank you.
Okay. Okay. Okay.